Any homework or anything like this? All right. What I want to do today, I'm going to give you a quiz as soon as I want to start S parameters, all right? Now, how many know what they are if you use S parameters? How many remember H parameters in transistors? Do y'all remember those? Do you remember GM, the transconductance? Do y'all remember these things? H parameters, they were port parameters. What I want to do is start by going over standard type of, if you got your, just bring down your project to I want to go through and show you the standard way that this is done. Now remember, we're talking about microwave engineering. Do you have a question?
No, sir.
Okay. If anybody does, just interrupt me. So this is S parameters. It's the next section. S parameters they're ubiquitous everywhere. When you do any kind of engineering at the high frequencies and stuff like this, you're going to run into them. So here's what it boils down to. You're going to have a block here, and it'll be called S parameters. Well, really, I'll just put it like this. This is what they really look like. It's a square matrix that has S11, S12, S21, and S22. Over here, you're going to have a transmission line with some characteristic impedance Z naught. Out of that, you're going to have a characteristic impedance Z naught as well. Two transmission lines. This is called port 1, right here, and this is port 2. There can be as many ports as you want. Now, at port 1, remember this is a transmission line, a coax cable, it could be a microwave waveguide, it could be any of these things. You're going to assume you have an incoming voltage as such that would be V1 positive, and there will be reflected voltage at port 1, V1 minus. Did you all see this anywhere before in your labs at all? Nothing? All right, so just think about this. Something goes in, something reflects. But there's also going to be a voltage coming into port 2, V2 plus, and a voltage reflection, V2 minus. Now you'll notice there's no electric fields indicated. These are voltages measured from the two conductors, like the inner conductor of a coax to the outer, and they vary versus distance down the actual cabling. So the relationship between these parameters is given by these parameters, the S parameters. A lot of times you'll just see a solid block S there, a big black S. That means it's a matrix. And something else before I continue, you don't need just two parts. They might be one port coming in, two ports coming out. You know what splitters are? When you take coax cable and you feed more than one TV or things like that. That's a standard type of S parameter device that we get to characterize. So when we deal with S parameters, the equations that dictate this for a two-port would be V1 minus is equal to S11 V1 plus S2, or S12, pardon me, S12 V2 plus, and then V1, or V2 minus is equal to S21 V1 plus S22 V2 plus, and in general it's given as this. V, regardless of the number of ports, is equal to some matrix S, and this would be V minus, is equal to some matrix S times V plus. That's the way it's a lot of times written. And you'll see this sometimes like this. Now these are two column vectors, and they're saying the output in each terminal has to do with the inputs at every other terminal. That's all it is. Follow me? All right, now, how do you go about determining these? And this is the part where I have to give you concrete examples. But when you're dealing with S parameters, these are things that are measured when they actually characterize the device and they put it up there. You have to understand what they are, versus frequency. When you look at S11, it's really V1 minus over V1 plus, assuming V2 plus equals 0. Now, what that means is this. It's the reflection coefficient. That's all it is. If you have this port, now they call it a matched, if this has got a characteristic impedance Z naught, and I terminate it onto Z naught, now listen to this point, this is an important point. Then anything that comes in here, some of it's gonna get out, but nothing will be reflected back this way, so there is no V2 plus. Y'all follow me on that, class? I'll do an example. How many understand that? If it's terminated, if this is terminated into its characteristic impedance, the reflection coefficient is 0 at the load, and therefore there is no V2 plus. And you can put down here that port 2 matched. All right? So, that's S11. And if you look, it makes sense. If I divide by V1 plus, right? And I assume V2 is 0, it is S11. Y'all follow me? This is just the reflection coefficient, by the way, when that's the case. That's the reflection coefficient of port 1 if it is matched. Do y'all follow me on this? Now, if it's not matched, it's not, but almost always it is. Now, I bet you can guess this. What do you think S22 is? Well, that would be V2 minus over V2 plus, assuming V1 plus is 0, right? In other words, now port 1 would be matched. And we'd be driving port 2 to look at the reflection coefficient. Do you follow me on this? It's going to seem trivial, but it isn't. And this would be port 1 match. All right. Now we get to S21 and S12. You all know what voltage gain is, right? When you had your microelectronics course, you calculated input versus, or output versus input voltage ratios, didn't you, class? That was considered the forward voltage gain. How many remember with transistors you also had reverse voltage gain? You remember that? Reverse voltage gain, both of which are important ideas to understand. So when we talk about voltage gain with S parameters, S21 is equal to V2 minus over V1 plus, and this is assuming that V2 plus is 0, and this is called the forward voltage gain. Now that should make sense. If you just look at this, V2 minus is coming out of port 2, V1 plus is going into port 1. So this is the forward voltage gain. If for whatever reason, S21, say it was 10, that if the first voltage coming in was 1 volt, the output would be 10 volts. That's all it means. There's nothing more to that. One thing I'll tell you, these S parameters are functions of frequency. And when they do measurements on these port devices, they use something called a network analyzer. How many have heard that term? Network analyzers. You will get familiar with them. Do your labs use them for anything? Do you use spectrum analyzers? All right, spectrum analyzers is really, it's just looking at one port at a time. But 2-port devices use S parameter measurements, and they'll show you S11, S22, S21, and S12 versus frequency. And that's real important. That's what you get on a data sheet. If anybody's ever buying components, when you get like chips for high frequency work, microwave work, you'll see that on it. And they'll have a lot more information, but that's the primary, because you want to know what the voltage gain is on the range of frequencies you deal with. So what do you think S12 is? Well, that's what? V1 minus over V2 plus, and this is assuming V1 plus is 0, and this is the reverse voltage gain. Of the system. Are y'all with me? So really we're talking about terminologies that you're familiar with, only S is not something. I believe S, and I'm not certain of this, came from system parameters, all right? How many have heard of A, B, C, D parameters? How many have heard of G parameters? When you didn't you do transconductance, GM, and you did these things, you did H parameters, right? All these type of things are just methods to characterize input versus output for a 2-port or more system. That's all they are. As a matter of fact, I did years ago, when I was up at NASA as a faculty, I fell out to my student who's got a PhD and everything. we worked on something where we had layers of material where we get S parameter measurements on. And we could back out from the S parameter measurements what those materials were. And it was a rather interesting time for me because I never really dealt with high frequency S parameter measurements for analysis, right? Until that point. It was reverse engineering what was inside of this stuff. So now I want to give you an example. Because anytime you see something like this is pretty abstract, you're really not familiar with it. The single best way to find out what it means is through a couple examples. So remember, what we want is the S parameters of this system. Here's the system. It's going to be just a coaxial cable, or a transmission line, say. Z naught on port 1 is going to be 50 ohms. Then right here, I'm going to put some lumped elements. These are resistors, capacitors, or inductors, and they're viewed only as the lumped element. There's no transmission line. I'm just going to put a resistor here, and I'm going to use this to be 25 ohms. And then I'm going to put a resistor here. I'm going to let this be 50 ohms. And then I'm going to connect it to another transmission line here. Z naught is 50 ohms, and this is port 2. Okay? We want, this is a kind of a typical question I get on final exam, something really almost a template problem on a final. They won't be just two resistors, but so here is the device I want the S parameters for. Y'all follow me? Now please watch this carefully, and I'm going to erase that because here's where trouble sets in for a lot of people. You'll notice I don't put any termination. I just have 50 ohms there. Follow me on that? It's assumed in any reasonable device that it's terminated into 50 ohms. If it isn't, then you got a fouled up system from the get-go. But it doesn't have to be.
Why is it assumed that it's terminated into 50 ohms?
Because if it wasn't, then you would get V2 plus coming back, right?
Okay.
All right, you want, every time you do microwave engineering, you always make sure the load impedance is equal to the actual transmission line or waveguide impedance. If it's not, you've created a horrific problem for yourself.
Okay.
Okay, so for this one, I want S11 first. I know the definition says it's V1 minus over V2 plus, assuming V2 plus equals 0. That means it's terminated, or it's not going to have any reflections from the load, and that can be given as the reflection coefficient of port 1. Let's talk about that and do it. Now, if you're doing reflection coefficients, what are you always looking for? You're looking for the input impedance, right? Isn't that the key thing? Because reflection coefficients are always what? They're the impedance you're going into, in our case, Zn on 1, port 1, minus Z naught over Zn on port 1 plus Z naught. Do you all agree with that? Yeah.
I think it's supposed to be V1 plus.
Yes, it is. My bad. You're absolutely right. I'm trying to get through this and I'll slow down.
I was wondering.
I usually don't have problems sitting and watching, but today it's jammed up under my slip shirts. All right, I got 12. All right, so
That's what I got.
how do we get Zn plus here? Now, pay attention to this. Here's where people foul this up. All right, I'm looking right here. I want the input impedance. You see how it's 25 ohms is in series with whatever, right? Now look, there's 50 goes to ground, but there's 50 ohms on that line. They are in parallel. Y'all hear me? So this would have an equivalent of 25. Y'all see that? Y'all see it in the back there, guys? All right, that means the input impedance, 25 and 25, or 50, right? What do you notice happening? S11 equals the reflection coefficient for 1. Now I have 50 minus 50 over 100 or 0. That is ideal. That's what you'd like. There's no reflection. That's not always true. A lot of times there's a minimal amount, and then these S parameters, they'll take 20 times the log of them, because when you get down to things that are like tenths of a ohm, hundredths of a ohm, and you're comparing that to things that are of the order of it, I shouldn't say of ohm, ratios that are that small, and you're comparing in the S parameter matrix something that's got a value of 10 or 100 for a voltage gain, then the scale is just way out of proportion, so they'll take 20 times the log of these quantities, the S parameters. Anyway, y'all agree that's 0? All right. While we're at it, let's get S21. That's V2 minus over V1 plus, and that's assuming that V2 plus is 0 or it's matched. Now this part I want you to pay attention to, because this does cause confusion. All right? Now, we're going to assume that we have plus to minus V1 plus coming in. Do y'all follow me? It hits here, right? Now, something you're unaware of, there's a transmission coefficient between this region and this region. That transmission coefficient 1, by definition is 1 plus the reflection coefficient of port 1, isn't it? In our case, it's nice because it happens to be 1. Reflection coefficient 0, transmission has to be 1. Y'all follow me? And that means transmission coefficient of port 1 is 1. So if I have V1 plus here, V1 plus appears here as well. Y'all see that, class? The transmission coefficient is 1. It means the transmitted field is just tau 1 is 1 times the incident field, which is V1. Go ahead.
Yeah, if it was anything other than 1, it would be V1 times the trans.
That's right, and I'm going to do an example of that. You'll see this when we do the port parameters on 2. All right, now, what happens when that voltage gets here? Just take a look. I have a series resistance of 25 ohms, and isn't this really equivalent to 25? How many see that I would have exactly what? It would be 25 over 25 plus 25, or 50. 25 over 50 times U. So I could say right here that V2 minus is going to be 1/2 V1 plus over V1 plus, or it's simply 1/2. Y'all follow me on that? That's the forward voltage gain. Whatever voltage comes into port 1, half of it will come out of port 2. Y'all follow me? Good question is what happened to the rest of it? It was dissipated in heat because of the resistances. Now, if you had inductors and capacitors there, you would never have real power dissipated. All right? But there could be a phase change so that the output voltage will be slightly different in phase and magnitude. We'll get to that later. I'm just letting you know that's where that power went. So that's 1/2. I've got S11, S21. Now what about S22? Somebody else. That's reflection at port 2. That would be V2 minus over V2 plus, assuming that V1 plus is 0. What's that going to be? Now take a look here. Make sure you see this. It'll help you if you just pay attention now. I need what? I need the Zn right there, don't I? Zn on port 2, class. Y'all with me? I have to get that to do this right. So what is that Zn going to be? Now look. You see there's 50. You're jumping off that transmission line. You're right. You see you got 50 in parallel with something right off the bat. Y'all see this? What's it in parallel with? Well, 25 that's in series with 50. So this second transmission line looks like, or this first port, 50 ohms to ground, but it's got that 25 here, and then from here down to ground, I have another 50, right? And I want the input impedance to cross those two, so it's really 75 in parallel with 50. Do y'all see that? Class D? okay? So what's that gonna be?
30.
You're right. It would be equal to 1/1/75 plus 1/50. And that will come down to 30 ohms. Y'all agree with that? Common denominator can be 100 downstairs. I mean, not 100,
Could do it with 100.
yeah, 150. And you're gonna get 2 and 3, but that's what it comes down to. So when I get this, 30 ohms, what does that make this reflection coefficient of port 2 or ST2 class? What am I going into, class? How many ohms? Port 2, looking this way, we just got it. How many ohms?
30 ohms.
30, right? It's going in at 30. I came from 50 over 30 plus 50. Or here, it's going to be what? Minus 20 over 80 or minus 1/4. Do y'all agree with that? All right, so here, I know that if I'm starting to make my S parameter matrix for this, S11 is 0, right? S21 is 1/2. S22 is minus 1/4. Now we need this guy. We need S12, which is V1 minus over V2 plus, assuming V1 plus is 0. And how do we get that? I want you to all pause just for a second and think about my question. I want to figure out what that is, right? Isn't that exactly what we did on port 1, only I'm now looking at port 2? And what was the key thing to get right here? I need to get the transmission coefficient here, John. Remember, I want to figure out what the transmission coefficient is on port 2. And what is the transmission coefficient on port 2, guys? 1 plus what? The reflection coefficient on port 2, right? Which would be what? Reflection is minus 1, so it's 3/4. Do y'all agree with that? All right. So the transmission coefficient, and I'll put it here on port 2, is 3/4. Now we're going to go through calculating this. So if I have a voltage waveform coming in here, and it's V2 plus. Now I want you to watch this. Believe it or not, this is one of the things that people, I think, are just casual about, and they blow this left and right on exams. So I got that coming in, V2 plus coming in. Then I have to multiply it by the transmission coefficient, T or tau 2, to get this voltage, which is right here. You all see that? So that voltage is going to be tau 2, that's on this resistor, times V2 plus. Now I want to break this, actually I'll do it right there to show you what I'm talking about. I could have drawn it right there. So I have this much voltage, I have tau 2 times V2 plus across this 50 ohm resistor. Right? But that isn't the end, because this is 25, and what I really want is the voltage here. Y'all follow me? This would be port 1, this would be port 2. Y'all see how it's going, class? In the back? So that means this voltage right here, plus or minus is that. What's this voltage going to be, guys?
Over 3rd.
You see how they're in series?
2/3.
This doesn't matter, does it? That 50 ohms is in parallel with it. So it's going to be tau 2 V2 plus times 50 over 75, isn't it? So that means S12 would be the transmission coefficient. I'll write it down, that 2, as such, times V2 plus, right? Or, V2 plus. And then it's going to be times 50 over 75, or 3/4. So the transmission coefficient was 3/4, right? Then this is 2/3, right? And then it's times V2 plus over V2 plus. They'll always cancel. And so I have what? I have the 3's cancel and I have 1/2. You all agree with that? Class? All right, so it's 1/2. And that means this is the actual S parameters. Now, it's a very simple example, but it really shows you how to go about business and calculate. I want to tell you, you can have as many ports as you want. You can have a 3-port device, 4-port, an N-port device. Typically what they're used for is to take a signal, high-frequency signal, and split it into different things. With radar, you're going to have some of the signal going to an antenna for transmission. Some of the signal will actually go to digital signal processing equipment, stuff like this. But this is really what they're used for these are the switches primarily. Okay, so that's S parameters in a nutshell. Want to do one more simple one, all right? Just to try to underscore this. And I know we're getting ready to go on Thanksgiving break. I put this out here for one reason. If I at least get it in front of your face now, give you a few problems, you'll be thinking about this probably, not consciously, but subconsciously. And when you come back, I won't have to start from scratch right now. All right? This one is going to be short and sweet, but I want to make sure you see it. Here's my device that I want the S parameters for. A simple capacitor. This is port 1, this is port 2. I'm going to make the capacitive reactance minus J 50 ohms. But then I'm going to make these, the transmission lines, Z0 equal to 100 ohms here, and Z0 over here equal to 100 ohms. And I want the S parameters associated with that, right? So you were just introduced to this. We know incoming signal would be V1 plus, reflected signal would be V1 minus. Here, transmitted signal would be V2 minus. Incoming signal would be V2 plus, right? I'm just showing you what I did before just to get that picture in your mind. It's smart to do this a few times until you get good at it. Then I'm going to say that V1 minus is actually equal to S11 V1 plus S12 V2 plus, and V2 minus is equal to S21 V1 plus S22 V2 plus. Now, I want you to go ahead and help me do this part. So, I want to calculate S11. You were just introduced to that. Think reflection coefficient. S11, S22, reflection coefficient. Are you with me? So if it's reflection coefficient at port 1, how would you get it? What's the key thing? What do you know about reflection coefficients on port 1? You need one piece of information right off the bat. Input impedance from port 1 looking into the S parameter device. You with me? So I need Zn, right, on port 1 minus Z0 over Zn port 1 plus Z0. What will that be? What is Z in port 1 anyway? Just like
50 minus J 50. 100 minus J 50.
I'm looking here, right? Right? I'm going to have this in series, right? Minus J50 with this, 100 minus J50. Correct, class? So this would be equal to 100 minus J50, right? Minus, and then the characteristic impedance is 100 over what? The sum of those, or it would be a 200 minus J50. Y'all with me? I'm just doing the math here as simply as I can. Agreed, everyone? Well, you can see on top, the hundreds kill each other, and I'm left with minus J50. We won't have to do this, because we don't have enough time. Over 200 minus J50, you can divide by 50 and you have one. Minus J over 4 minus J, right? You can leave it at that, but that will be a magnitude and a phase of S11. Now there's something I didn't say, but I bet you know what it is. What is S22? And give me your reason for it.
It's the same as S1.
She's absolutely right, because if you look at it either way, it's the same. It's called a symmetric matrix or symmetric S parameters. Whatever they are in port 1, just reverse it. It's the same thing. They are in port 2 as well. Y'all follow me? So you only have one half the work. So S11 will be equal to S22. Now, what is S21? S21 is equal to V2 minus over V1 plus, assuming V2 plus is 0. That's the forward voltage gain, isn't it? Guys? All right, so what is it? Well, here I'm going to have my V1 plus coming in, and what am I after? I'm after the voltage just on the other side of that transmission line. Remember, the voltage just on this side isn't this because there's a reflection coefficient. Some of it's reflected back. The sum of the reflected voltage and the incident voltage is the transmitted voltage. So here it would be a transmission coefficient at port 1 times V1 plus, correct? Y'all with me? All right. Well, how do we get the transmission coefficient? If this is the reflection coefficient on port 1, which would be minus J over 4 minus J, I'm going to just leave it as that. What would I do to get transmission, guys? Just add 1 to it, correct? I get transmission, correct, class? So, now I'd say, and I'll do it here, this is the last point I'm doing that. Transmission coefficient of port 1 would be 1 plus reflection coefficient of port 1, or it's 1 minus J1 over 4 minus J1. You could say this is really 4 minus J1 minus J1 over 4 minus J1 if you wanted to, and you would have simply 4 minus J2 over 4 minus J1. And that would be, and I'm not even caring about the magnitude and phase of that. I'm just showing you the method. It'll come down to a magnitude and a phase. Everybody okay with that? So, now that I have that.
Shouldn't that be plus, not minus?
Pardon me?
'Cause it's,
No, it is. Look, this is a minus J there, right?
oh, yeah, sorry.
Yeah, I know where you're going with that. It was a minus J already. You're absolutely right. It's not subtracting. So now that I have that, I can see that my S21 is going to be this, tau 1, I'll just leave it at that, times V1 plus, and then what happens? Once I have this voltage right here, how do I get my output voltage?
Voltage divider.
Yeah, think that this is just 50 ohms to ground. 100 ohms to ground, right? So it would be what? It would be this voltage, tau 1 V1 plus, times 100 over 100 minus J50, right? So it's going to be this, and then it's going to be times 100 over 100 minus J50. We can clean that up, we can do whatever we want, but would not S21 be S12 as well, class? Because of the properties of symmetry? How many see this right here? Okay, any question? All right. Well, you're anxious to go on break, I understand. So, how about we populate this row? You can stay where you're at.
Nope.
All right, vacate this row, sorry. Populate this row.